So this is the first lecture on ordinary differential equation. So I guess you all know some basics of ordinary differential equation. So in this lecture I will not go into this like order, degree, such kind of thing. I am going directly to first order differential equation. So we will explore methods of how to solve this first order ordinary differential equations. So among these actually we have two types. One type, or first type, they are called exact equation, for which exact solutions are possible by different methods, and another is separable equations. They are basically more easier than exact things, exact equations, and those are basically you can solve very easily by separating out those variables. So I'll discuss them. So first I am going to tell you how to tackle or what is exact differential equation and what are those methods by which you can solve these exact equations. So basically, you know, any differential equation, first order, we are just taking this first order differential equation. This dy dx equals to f of xy. It is a function, you know, and you already know that this x is independent variable and y is dependent variable. So this is a kind of first order differential equation. So our task is to solve this type of equation, or which type of first order equations are exactly solvable by the methods. So sometimes you will encounter this type of equations, or sometimes you will encounter such kind of equations. This is actually differential form. Both are actually equivalent type of thing. So if you take dy dx is equals to f of xy, then you can easily write it down in this form. Okay, so sometimes I will say this kind of first order differential equation, or sometimes I will tell you about this thing. Okay, so let us first take an example. So first example is this kind of thing. So dy dx is equals to x square plus y square divided by x minus y. So you all know this thing. You can easily write in this way. We just move these things in diagonally and you can easily get this thing. So these two types of things are equivalent. So that's why I have written this symbol. This is equivalent symbol. Okay. So any differential equation which is of this form, you can at once write its differential form, which is this. Okay. I think this thing is very easy for you to understand. So now, what is exact differential equation? So I am telling you again and again, exact. But what is exactly this exact differential equations? Okay, so this is the question. So to answer the question, we first tell you that what is total differential of a function. So let f be a function of two variables x and y. Total differential of this function is denoted by d of f, and this is written in this way. This is del f del x in del dx plus del f del y into dy. Okay, so this kind of thing, this is called the total differential of this function. I think this type of thing you have already encountered, you all know. Okay, so now we take a differential equation in its differential form, and let us consider this expression m dx plus n dy. Okay, this expression m dx n dy. If you look at the example, things will be clear. Okay. Now this thing is called exact if there exists a function f, function of two variables x and y, such that if you differentiate this function with respect to x partially, you get m, and if you differentiate it with respect to y partially, you get n. Okay, so this thing, this differential thing, this thing is called exact if there exists a function f such that this thing happens, in that case we can write this df. You all know that df is this kind of thing. Now del f del x is m and del f del y is n, hence we replace this by m and this by n, and we can write this total expression m dx plus n dy, that is our given expression, you can write as a total differential of a function f. This is total differential of a function f. So I am again repeating, this type of expression is called exact if there is a function f such that this differential thing can be written as a total differential of a function f. So this kind of thing holds where this holds. Okay, so then we say this equation, this given differential equation m dx plus n dy is equals to 0 is exact differential equation. So you just first at once take this part out, this differential part out, and check if there is some function f for which this x derivative, all the derivatives are in partial terms, and if this y derivatives satisfies this type, this thing, del f del x is m and del f del y is n. So if this is possible, then we say that this differential equation is an exact differential equation. So I think you need an example for this. So very first example I can give you is consider this type of expression. Okay, y squared dx plus 2xy dy is equals to 0. Now compare it with m dx plus n dy is equals to 0. We have m is y square and n is 2xy. Okay, you compare it and you will get m and n, this thing. Now partially you can obviously differentiate this m partially with respect to y, and you get this is del del y. Now you know this m thing is del f del x. So this kind of thing you can at once write, if you interchange x and y, you can write in this way, and this is again del n del x. Okay, because this is n. Okay, so this thing is n, so you put it here, this is del n del x. Okay, so this is a very important step. You should remember that for a differential equation, if it is exact, or we can say for an exact differential equation, this relation holds. And conversely, if this thing holds for an differential equation, then the differential equation should be exact. So this is the condition for checking whether a given differential equation is exact or not. So actually there are some underlying certain conditions for which this type of interchange is possible. You remember that I have interchanged x with y and y with x. This type of interchange is possible only when there is continuity of first order partial derivatives for the function f. So this type of things are already there. So you just remember that any first order differential equation which is of this form, m dx plus n dy is equals to 0, this kind of equation, this kind of first order partial differential equation, this is exact whenever del m del y is equals to del n del x. This is very important condition. This holds in both ways. That is, it is a necessary condition and sufficient condition. That means if this holds, then the given differential equation is exact, and if the given differential equation is exact, then this kind of relation holds. So this type of relation comes from this thing. Okay, you should remember. So now the example I have given, this example where m is y square and n is 2xy. If you differentiate m with respect to y, you get 2y, and if you differentiate n with respect to x, you get 2y. They are equal. Hence this expression or this given differential equation is exact. Okay, so actually this relation, by this relation we actually bypass the need of constructing this type of f function, and we just verify only by this equation without ever constructing f. So we just bypassed f through this relation. We have del m del y and del m del x. We have relation between m and n. Okay, so again I am going to tell you a theorem. Actually is very important result. So now you have an equation, you have an first order differential equation, you know how to check whether it is exact or not. So now the condition, the theorem tells that the solution of exact differential equation, the exact differential equation means this type of equation, the solution of this equation is f equals to c, where what is f? F is that function, this differential function. This f is the solution of the given differential equation, this. Okay, where obviously del f del x is m and del f del y is n. So here we have bypassed the need of the function capital F, but somehow this function, this capital function capital F is needed to solve the given differential equation, this. Okay, so in the solution you can't bypass, so you have to find the f. But when someone said please check whether this given equation is exact or not, you can at once do this by you can at once verify from this relation. But if they further ask that what is the solution of the differential equation, you can't bypass f. So you have to find f, and that f is equals to c. C is any constant, arbitrary constant, is a solution of the differential equation. Okay. So I have told you to type of very important result in this regard of exactness. So I think it's time to give some example and show you how to solve first order ordinary differential equations which are exact. Okay, so this is our given equation, 3x square plus 4xy dx and 2x square plus 2x square plus 2y dy is 0. This is our given equation, and I guess you can do on your own that this given equation is exact. So your task is first to identify what is m and what is n. This is m and this is n. Now I have said an equation is exact whenever del m del y is equals to del n del x. So you have m in your hand, n in your hand. So we can find del m del y and del n del x and check they are equal. Okay, so if they are equal, the equation is exact. I am telling you that this thing is exact, but you should need to verify it on your own. So now we have m equals to this and n equals to this, but since this equation is exact, there is a function f such that del f del x is m and del f del y is n. So del f del x is m equals to this thing, because you know that del f del x is equals to m and del f del y is equals to n. So we have this relation. From this relation you can integrate f. So now if you integrate f, f is this thing, f is this thing, and this is simply this. Now if you ask me why or what is phi of y, So remember, you have differentiated it partially. So if there is y, you have treated it as constant. So whenever you integrate it or you do the reverse operation, so this type of function can come, because this type of function, if you differentiate, it will become 0. So this type of function reverse, you will do the perform the reverse thing, that is integration. This type of function can come. Remember, if you done integration, normal integration, here some constants come, but in this type of partial differentiation thing, the constant will be nothing but a function of y, because any function of y, if you differentiate it, it becomes 0. So this should come. Okay, so we have this kind of thing. Now we have this thing, f is this thing. Now we have f. Now if you partially differentiate f with respect to y, you get this thing. X cube will vanish to x square y. If you differentiate it partially with respect to y, this becomes 2x square, and this phi y becomes phi dash y. Okay, because you are partially differentiate with respect to y, and this is function of y, so it will become actually phi dash y. That means d phi dy. Okay, so now since this equation is exact, we got del f del y is this, but we know that del f del y in n is equals to 2x square plus y. So we can put it is 2x square plus y, this thing. So 2x square cancels out. So we have phi dash y is equals to 2y. Now if you integrate this thing, then you get phi y is equals to y square plus c. So basically we know phi dash is nothing, phi dash y is nothing but d phi dy. So if you integrate this thing, you will get phi y is y square plus. Okay, so you can do this same thing with respect to y. That means here I have started from this expression del f del y, integrate this thing, and then again differentiate with respect to y, then equate it with this thing and get the phi y. So you can start it from here, you can integrate this thing, then you can again differentiate it with respect to x partially, and then you can equate this thing with if you actually have shown, if you eat this thing, if you integrate this thing, you will get this thing, this kind of thing. But here again you should remember that this function should be there should be some function of x, and if you differentiate it partially with respect to x, you can do it and then equate it with this thing, and you can then solve this phi. So you have this form of phi, and if you put this here, you will get the function f is equals to x cube plus 2x square y plus y square plus c. So this is the solution. Okay, so this is our f. So this is our basically f equals to c is our solution. Okay, you know the last theorem, if you remember, that what is our solution? F x y is c is our solution. So this thing is our solution. Okay, so now I'll discuss what is integrating factor. Okay, so let us take an equation m dx plus n dy is equals to 0, and guess it is not exact. So what if it is exact? If it is exact, then we can do these previous things, and we can go on like this sum and get solution. So now if this expression is not exact, so what can we do to solve it? So if this is not exact, let us consider there exists some function mu. Mu is not constant here, but a function of both x and y. This can be a function of x and y. So if you multiply this expression with mu, the situation changes and this thing become exact. Okay, so we have this differential equation is not exact. We multiply it with by mu and the resultant equation become exact. Resultant equation means m dash dx plus m dash dy is 0 is exact, where basically m dash is mu into m and m dash is equals to mu into sorry, it's not mu, mu into n is n dash. Okay, so consider an example. So let us consider this expression. You can at once check this kind of equation is not exact. This is m, this is n. You can at once check del m del y and del n del x. If they are equal or not, you will see that they are not equal. But you can check this mu is equals to x square y is an integrating factor of this equation. So what is mean by integrating factor? That means if you multiply this thing with this thing and multiply this thing with this thing and consider the new m dash and n dash. So now if you take del m dash del y and del n dash del x, actually this kind of exactness checking with respect to m dash and n dash, so you will see that they are equal. Okay, so this is the power of integrating factor. This thing kind of thing is called integrating factor and is the power. So now before going I will explain some methods, actually some form of integrating factor which you should keep in mind, and they will help you to guess the equation, they guess the integrating factor from equation itself. Okay, so I'll tell you the methods, but before going into that, this integrating factor things, I just first mention you the separable equations. Please remember that when I have started this lecture, I have told you that there are two types of equation. Like number one is exact and second one is separable equations. These separable equations are basically very simple, very much simple. Separable equations are nothing like it is a very simple kind of thing, this kind of equation, because you see this m part and n part both are factorized into x and y separately. So you have a function of x, function of y, function of x, function of y, they are separated. So if you have given this type of equations, solution of these equations are very easy, and you can just rearrange the terms. You put it here and put it there, and it's actually reshuffling this equation, and you can easily at once integrate this thing out, and it's very easy thing. So now you can also check that this kind of equation is not exact, but if you have this kind of equation, you can at once write the integrating factor is this. You can check if it's integrating factor, just multiply this thing with this thing and multiply this thing with this thing, you get m and n, and check they are exact. Okay. For an example, I have given this type of separable equation. So they are actually separable equation. That means you can actually separate out this thing. If you divide by y to the power 4 both sides, this cancels out and y to the power 4 comes here, and again if you divide by x cube goes from here to there. So this side becomes total function of x, and this I think will be function of y only. So you can integrate the things very easily. So in this sense, these separable equations can be tackled more easily. But you can also check this thing actually is the integrating factor. If you multiply this thing by this thing and multiply again this thing with this thing, and if you take new m dash and n dash, and if you check del m dash del y is equal to del n dash del x, you will see that they are equal. Okay, so you can see that separable equations you can solve very easily. Also there are some other equations which are there are some methods by which they can reduced to separable equation. They are not looking like separable, but they can be reduced to separable equations by some substitution kind of thing. So in this regard, I am explaining a theorem. This is a very important theorem. It says that any homogeneous equations m dx plus n dy is equals to 0 can be transformed to a separable equation by change of variable y equals to vx. So if this equation is homogeneous, then this equation can be transformed to a separable equation by this kind of transformation. So now, what is homogeneous equation? Homogeneous means this kind of equations can all be written like dy is equals to fxy. Now this f thing can be written as a function of y by x. Okay, if this happens, then we say that this equation is homogeneous. So homogeneous first order equations can be transformed into separable form by means of this transformation y equals to vx. Okay, let us take an example. So you have this equation, right? So now dy dx is equals to 3y square minus x square by 2xy. Okay, you can write it. It's very easy. Now if you can check it that this equation, or sorry, this expression can be written in this form. This is 3 by 2 y square by xy, y cancels out, this becomes y by x minus half x square by xy, that means x by y. Now x by y can be written as 1 by y by x. Okay, so this kind of thing. So this equation is homogeneous. So now this equation can be transformed to separable form by this substitution. I think you can do the substitution this thing and solve this equation. So how to substitute? You have y equals to vx. Now you know dy dx, this is equals to v dx ddx of x plus x dv dx, that is it is v plus x dv dx. Now substitute this thing here and substitute y by x as v. This is 3 by 2 v minus 1 by v. Now you can, I think you will be able to solve this equation. You have done it earlier in your, I think in 11 12. Okay, this will be a very simple equation to solve. You will solve it. Okay, solve. So now I think I will explain, or I will tell you any first order linear differential equation. First order linear differential equation can have this form: dy dx plus pxy plus qx. Okay, this is the standard form of first order ordinary differential equation, which is both linear in x and y. Okay, so this is a very standard form and you will encounter it numerous times. So please remember, this dy dx is plus pxy is equals to qx. This is the first order ordinary differential equation. So if you have to solve this equation, so I think I'll leave it to you to how to solve this equation, because you will check it with your book or you can do it on your own. So this kind of solution we can anytime you can solve this kind of equation. So what is the solution and how to solve it, you can check it through book. And please do these two sums if you are able to do that, or if you are not able to solve this equation, or you are not able to understand how to solve this equation, please tell me, because I am also leaving another thing which is very important, is Bernoulli equation. This is like dy dx plus pxy plus equals to qx into y to the power n. So this type of equations is due to Bernoulli. So he proposes methods to solve this equation. So again, this kind of equations can be solved very easily. So I have also given two examples. You can also consult your book. This is very standard method or standard way of solving this equation. So if you are not able to solve this equation or not able to understand, please tell me. I will explain these two things in another lecture. Okay. So right now I am just going to mention few procedures or few ways by which you can find integrating factor differential equations. So you have given a non-exact differential equation. So by looking at this equation, this is m dx plus n dy is equals to 0. By looking at this equation, you can at once say the integrating factor. So there are some methods, some technique. So first one is, you have given these equations and now you check 1 by m del n del x. First you have given some equations and you identify what is m and what is n, and then you check this thing 1 by m del n del x minus del m del y. If you check this thing or simplify this thing, if you get this thing as a function of y only, there is no x, there is no x is involved there in this expression, only y part is there, that is a function of y only. You can say this is phi 1 y. If this happens, then the integrating factor of this equation is mu1, which is basically e to the power integration phi 1 y dy. What is phi 1 y? Phi 1 is nothing but this expression, provided this expression or this function is a function of y only, there is no x. Okay, so likewise this similar thing happens. So you can also check if 1 by n del m del y minus del n del x, if this is function of x only, then integrating factor mu2 will be mu2 is equals to e to the power integration phi 2x dx. Okay. So these two things you should remember in mind, these two form, and maybe you will see that if you calculate this thing, this is not a function of y but there are x involved, so this method fails. You will again check this thing. If it is function of x only, you are all set to go, then your integrating factor is this thing. But again, if it's not a function of x only, there are y involved, then you can't go even in this way. Okay, so these are some standard methods by which you can find integrating factor very easily. Not all the time, but sometimes. Okay, so for this we have given some examples. We have given this example of this function. We can check that for this equation, del m del y is 1, del m del x is 2xy minus 1, and if you calculate 1 by n del m del y minus del n del x, this thing simplifies and you will get minus 2yx. So this thing is function of x only, so this rule is applicable. So our integrating factor is e to the power integration phi 2x dx. So this thing is our integrating factor. If it's out, you will get 1 by x square, and if you multiply by this integrating factor, the equation becomes this thing, and now this equation becomes exact. Now you all know how to solve this equation, exact equations. The methods are known. Okay, so our intention was to turn out this non-exact thing to exact one, and then we have to then we will solve this exact thing. Third form, sometimes m and n are homogeneous functions of same degree, then integrating factor is 1 by mx plus ny. They are homogeneous functions of same degree. So what do you mean by homogeneous functions? A function is homogeneous if this is a given function, this function is homogeneous. You substitute tx in place of x and ty in place of y, and if you get this thing becomes this, if you get this t to the power n comes out and f of xy is again comes there. So if you get such kind of thing, this function is called homogeneous. For example, if you take if xy is equals to x square plus y square. Now what is if tx ty is nothing but you replace x by tx, this becomes t square x square, and ty in place of y, and this becomes t square y square. Now this thing you can take t t square common, and this thing become x square plus y square. Hence you see this is fxy is coming again. So we have f tx ty is equals to t square f of xy. So this n is, value of n here is 2, so the function f is undoubtedly homogeneous function of degree 2. So whenever such kind of thing happens with m and n, and provided both are homogeneous functions of same degree, then the integrating factor should be like this. Okay. Now again, if the form of m is given like m is y f of xy and n is x f2 of xy, this is not x comma y but it is a function of xy. Okay, similarly this thing is function of xy. So in that case, the integrating factor should be 1 by mx minus ny, and provided this mx minus ny is not 0. Okay, and there is another kind of things there, this kind of equation, this kind of thing involved. So the integrating factor can be like this, where this kind of things are needed. So I'm not going to discuss these things in very details, but you need to remember these two things and previous two things in very details. Okay, so I'm just taking an example of this kind of function, where kind of differential equation, where if you see that m is this and n is this, and if you calculate mx minus ny, this will come 3x cube minus 3x cube by 2, which is obviously non-zero. You can check it yourself. So our integrating factor is mu is 1 by 3x cube y cube. So this is actually this thing. This is rule 4. Okay, so now if you multiply this thing with this and this both, so our equation becomes this, and you can check this is exactly, this is an exact differential equation. This thing is m dash, this is n dash. You check and show on your own that del m dash del y and del n dash del x, they are equal, and you can solve this equation. Okay, and for the last thing, this I'm not going to discuss in great details, but I'm showing you a problem which you can solve very easily. So this type of problem comes in this way, that find an integrating factor of the form this thing of this. So in this problem they are telling you to find an integrating factor of this type of form. That means you take this is an integrating factor, you multiply this two thing and verify whether the equation becomes exact, or you find the condition of exactness of the differential equation, and from that we have to find the value of n and n. So you have this is an integrating factor, you multiply with this thing, you multiply this thing with this. This is our new m dash. You have got this new m dash, and also the value of new n dash, and now you can easily calculate del m dash del y and del m dash del x. We have the expressions, and you know this is an integrating factor, so the equation are exact. So you have del m dash del y is equals to del m dash del x, and from the relation you have to mutually check what is the value of m and n. Okay, so I think this problem I am leaving to you, but you should tell me if you are able to do this problem, because the problem is little bit trickier. Okay, sorry. So with this I am ending today's lecture. So these are the ways, because you should already remember that this rule 1, 2, 3, 4, they are very important, and these rules will provide you to find integrating factor of non-exact equations, by which you can solve these equations very easily. Okay.